filtering and digital pulse amplitude modulation for the class Real-Time Digital Signal Processing at the University of Texas, and this is the spring 2014 semester. So this is part 4. We have done already quite a bit of this is the last part of the 4. So we've already covered the transmission of one bit at a time, match filtering, PAM system, and the first part of communication performance on bit error probability for binary signals. For today, we'll do symbol error probability and eye diagrams. And if time permits, we'll come back and do intersymbol interference. Okay, so we left off last time with this derivation, which was the probability of an error for 2 PAMs, so 2-level PAM, 1 bit per symbol. And the probability of error reduces to a very nice formula, very compact formula. And that probability of error is this Markham Q function. And the argument is the square root of SNR. And what we'll see in all the derivations for larger constellations for PAM, we'll see it also for QAM, that this trend will continue. The argument will be some function of the square root of SNR, and the square root of SNR is in linear units, not dB. So it's in linear units, not dB. And you'll see here that I have some measure of the power, some average power of the transmitted symbol. Amplitude is the 2-level PAM, so the amplitude is either capital A or minus capital A. So the average power over the symbol time is A squared. And then there's some notion of some representation of the noise power. And this is given by the variance sigma squared. So this is a simple formula, and Q, as we've seen before, dramatically decreases. So the Q function dramatically decreases with increasing X, and that's on the previous slide. And that decreases it's pretty fast. It's almost an exponential decay. Here is a bound for that Q function, the Markham Q function, as a function of the square root of SNR. So it looks like exponential decay in SNR, scaled by the square root of that SNR in linear units. So as SNR gets large, this term, as we increase SNR by 10%, doesn't change very much. The big change occurs in the numerator because it's exponential decay. So a little bit of improvement in SNR is a huge reduction in the probability of error. Okay, so we'll see the same trend in the derivation for multi-level PAM, or more than 2 levels for PAM. Okay, so let's go ahead and set up the derivation for multi-level. For PAM, this will apply to even 2 levels. This is a more general case. So again, for simplicity, we're going to set the symbol time to 1 second. We'll come back and change that next week. There is an impact of the symbol time on SNR. The average transmitted signal power, a little more complicated now because I could have 4 levels, 8 levels. I could do 6-level PAM. Nothing wrong with that. Okay, there is a high-speed DSL. It's HDSL2, which is a DSL standard for business that uses like 7.2 bits or something PAM, 150 levels of PAM. So it doesn't have to be a power of 2. Good. All right, but generally it's a power of 2. So the average transmitted signal power, well, for the 2 PAM case, it's pretty easy. I mean, the average transmitted signal power, assuming we don't have to even assume equally likely transmission, the average signal power will be proportional to d squared, because my only 2 choices for symbol amplitude would be d and minus d. For 4 PAM, a little more complicated, right? So the possible power, so these are the amplitude values, 3d, d minus d, and minus 3d. So if I look at the power that each one takes up, this one's going to take 9d squared, this is d squared, and 9d squared. So the total power, assuming equally likely transmission among the 4 symbol levels, our values, I get 20d squared, so that's the total power. That means the average power is what? That divided by 4, so 5d squared, right? So average power So 4 PAM average power, you take the total power divided by 4, 5d squared. What's the peak power? 9d squared. So the peak power is proportional to 9d squared. Now there's a little more to the peak and average power. We also have at play, the amount of what's in the pulse shape that we're using. What is its average, power? So we're just going to normalize that to 1, just for convenience. So that our signal power is this, what's the expected value of the symbol amplitude squared? And we just went through that exercise for 2 PAM and 4 PAM, assuming equally likely values in our symbol amplitudes for transmission. Now, if I do this more generally for any number of levels, then I'll need 2 things. One is to figure out how do I generate these levels, D minus D, 3D, minus 3D, and so forth. Pretty nice formula for that. So if I know that the spacing between any 2 constellation points is 2D, then I can generate these levels by first enumerating over some range of values, capital M values, and then substituting into this affine relationship, and you'll see the 2 here. So you'll see that there's a 2D effect here. That's our constellation spacing. So we plug in some values. So again, let M be let M be 2. So when M is 2, I can be what? I can be what values? When M is 2, 0 and 1. So and if I plug in 0 and 1 into the formula for levels, I should get minus D and D. So if I let I be 0, then I get minus D. If I let I be 1, then I get D. Right? So it's a very nice formula, and this works for M, capital M is 4, and so forth. So it's a very nice way to generate these levels. You could use it in MATLAB. You can use it in whatever. So in our book, we have this built in as a built-in function that does it for us. Go ahead. Yeah.
But does it also work for like those decimal level PAM?
Yeah, this one is going to, I haven't tried it for 7.2 or 150 levels, right? But in principle, it should, because this M has to be an integer. So even for this HDSL2 standard, it's an integer number of levels. It just works out to some fractional number of bits. So as long as M is an integer, this should work. Now, also in this PAM amplitude, or in the PAM constellation map, we assume that there are symbol amplitudes, as many choices that are positive as negative. Right? And if they're equally likely, it also means that the average value is what? What's the average value here? 0. Right? So this is back to the issue that if we have equally likely transmission of these symbol amplitudes, then on average, our baseband signal for PAM modulation will have an average value of 0. If I observe over all time. Of course, over a small period of time, you may get some variations to that. But on the long-term average, it's 0. All right, next step is to figure out what's the average power in the signal, because we want to get back to some SNR measure, ultimately. This is our starting point for signal quality analysis. So the signal power is going to be what we had earlier. So the signal power is what's the expected value of the amplitude squared in this constellation map. And so I can basically compute the total power. So that's just the total power, just like we did before. And then I divide by the number of entries in the constellation map. That is, I divide by simply the number of levels for my PAM modulation. Now, I don't have to do I don't have to add all of them up because I have symmetry. So as long as I add, the positive ones or the negative ones, I'm good. I can just multiply by 2. So I do that here. So I just add up half of the entries. So I go from, I enumerate over the values of I from 1 to capital M over 2 inclusive. That's the upper half. In the constellation, I could have done the lower half just as easily. So here's the upper half, and then I plug in the formula for L sub I, and then I just take that squared. And the reason I do that is because I'm equally likely. So the expected value here, since they're equally likely, the total power is just, they're equally likely. So the total power is just the sum of the symbol amplitude powers. And then I divide by the number of levels. And if I run the finite sum on this one, you get a nice formula that's going to be related to 2 parameters. One is the number of levels, right? So M is the number of levels in the constellation. Usually a power of 2, not always. And then D, which is half the constellation spacing. And we'll be working with uniformly spaced constellations for QAM and for PAM. All right, we're still in PAM. So if I set the value of D, it tells me what the signal, so the signal power is proportional to D squared. So the bigger the D, the larger the D, the more, average signal power we need. All right, we're looking at average transmitted signal power. If I increase the number of levels and keep D the same, I also have an increase in the average signal power for transmission. Now in practice, standards will limit the peak power simply so you don't interfere with other services either in the same band or in adjacent bands. So there's usually an upper limit imposed even for an unlicensed band. Unlicensed doesn't mean unregulated. So even in Wi-Fi, there's only so much power you're allowed to put into the transmission band. So that is a limit to the transmit signal power, which limits D and the number of levels you can use. So it isn't like I can pick any value I want in practice. All right, so let's go after deriving the SNR in our case. So for us, again, we're going to assume that the only impairment is additive noise. So I have my transmission, I have additive noise. This is spectrally flat Gaussian. With 0 mean and variance sigma squared. At the receiver, it's going to go through a match filter. Match the pulse shape, and then I sample at the symbol time, and then I make a decision as to what bit pattern. So this is now an estimate of the amplitude. This is an estimate of the symbol amplitude, which will be the transmitted symbol amplitude plus some random number that relates to the noise that gets through the match filter. And I have to make a decision as to what bits had been transmitted. So now I get my symbol of bits that comes out of the decision device. So much noise power gets through to the decision device is depends on the amount of noise in the channel. So there's my channel model. It's just additive noise. And really how much of that noise gets all the way through the match filter and the sampling block. And remember, the match filter is a low-pass filter that's going to filter out the high-frequency noise, at least attenuate the high-frequency noise. So we're going to have a change in the noise power. Okay. So this noise power, this is now I'm looking at my, the power spectral density here. So the power spectral density is constant for all frequencies. And what I'm going to pass through are just the low frequencies. Now I'm assuming that earlier, if you remember, I assumed that the symbol time was what? To make it easy. What was the symbol time? 1 second. And that means that the symbol rate is 1 hertz. You got it. That means that the symbol, and that's in hertz, and then the symbol rate, I guess, in radians would be 2 pi. So that means that omega sim, the symbol rate in radians, is simply 2 pi radians per second to be more complete on the units. So if I look at this, I integrate, I'm only passing the frequencies from half the symbol rate to minus half the symbol rate. So I'm passing from minus pi to pi in radians per second. So I multiply by 2 pi times this constant, and then I divide by 2 pi. So I'm left really with just the variance getting through. Okay, so the power, I just pick off the low frequency part. Okay, so this is just to be, and the variance was n naught over 2, just from earlier. It's a historical approach to variance. The 2 sometimes goes away and sometimes it doesn't. Anyway, this is an older way of looking at it, but still valuable. So here's the SNR. I have, because now I know what my noise power is, it's just sigma squared. It gets through, still gets through. The match filter is what gets through the match filter. Remember, the match filter will scale the variance of this additive noise by its symbol, by its twice its bandwidth. The bandwidth is half the symbol rate. That means that we scale by the symbol rate. The symbol rate is 1 in hertz. All right, so I have signal power over noise power. I use the noise power formula on this slide and the signal power formula from the previous slide. And now I have a formula that depends on 3 things: number of levels, m, the half the constellation spacing, d, and n naught over 2. The 2's over here in the numerator, and that means that that's just the variance. So I'm proportional to m squared in terms of SNR in linear units. I'm proportional to d squared, and I'm inversely proportional to the variance of the noise in the channel. And so really, if I go back to this noise, this is really sigma squared times, in the end, f sim, which in our case is just sigma squared. But you can see the effect of the symbol time or symbol rate on this derivation. We'll come back and include it again next week. Now, if we assume an ideal channel, again, there's no memory, and there's no, it doesn't, so the channel does not introduce ISI. The only impairment in the channel is additive noise. And if we assume that, then what we'll see in this multi-level PAM case is exactly what we saw in 2PAM, that this estimate, this is really my A sub n in the block diagram. So the estimated symbol amplitude is the transmitted symbol amplitude plus noise. And this noise is really just represented by a random variable, because we only have one value at the end of each symbol time, and that's represented by the sampling operation in the block diagram. So we get one symbol amplitude per symbol time. And so it's a transmitted symbol amplitude that's been thrown off a little bit by the noise in the channel. That's it. And that amount of it's being thrown off is represented by a random variable that also follows a Gaussian distribution. So this V sub n has the same distribution, and more generally, this would be sigma squared times f sim, but our f sim is 1. Now, we have 2 possible ways we can make a mistake at the receiver for PAM. Okay, so if I have 4 PAM, I'll draw a 4 PAM constellation here. I have 4 levels, minus 3D, minus D, D, and 3D. And what the receiver is going to do is it's going to look at the value coming off the sampling block, this A hat of n, and it's going to threshold it. to figure out what's the closest symbol amplitude value. And for now, this decision is done once, and it's done. This is called hard decoding. Bam, it's just done. We don't adjust it later. So what's this threshold between 3D and D? What's that value? 2D. And again, we're assuming equally likely, so that's the right to use. We have 0 and we have minus 2D. So there are 3 thresholds to compare against at the receiver. (2D, 0, and minus 2D. How many comparisons do you think you would need to figure out what's the closest symbol amplitude? Good. 2. How would you get it to 2? Right, divide and conquer. So first compare against 0, see which side you're on, then do one more comparison to figure out which of the 2 remaining levels. Binary. It's almost a binary. It is like a binary search. You're reducing the search space by a factor of 2 each time. Now, for 4-level PAM, this is not a huge savings, but in DSL, we have 15-bit constellations with 32,768 levels. So if you did a linear search over, it would take you a long time. If you did it by divide and conquer, how many comparisons would you need for a 15-bit constellation? 15, which is great. Much better than 32,768 comparisons. Yeah, so the divide and conquer is the fast algorithm here. Okay, so let's go. So I have 2 possible ways to make a mistake. If I have the outer constellation point, well, let's do the inner constellation point. So I have m minus 2 in inner points or interior points in this constellation map, and I can make a mistake in either of 2 directions. Either the noise puts me, so if I look at an interior point here, so the noise can put me, if it's too positive, puts me out of this range from 0 to 2D in the positive direction, and if it's too negative, it puts me out of the range in the negative direction. So I get an error if, or only if, the absolute value of this additive noise term is greater than D in absolute value. And we know what that looks like. This is going to be, basically, I'm integrating a tail, so this is going to be a distribute, this really. So that the received amplitude is the transmitted amplitude plus a Gaussian random variable. So I'm going to get a distribution that looks something like this if I transmitted a symbol amplitude of minus D. So I'm going to get in trouble for that tail of the distribution and for this tail of the distribution. So that tells me how likely I am to make a mistake. So I need to integrate the tail of a Gaussian in both directions, 2 directions. So one direction, I get a Q function. That's the notion of the Q function. I integrate one tail. If I integrate 2 tails, I just multiply by 2 to get the 2 tails. Now, for the outer constellation levels, I only get into trouble in one direction. I have a lower probability of error, and this is where I would want to put, if my bits had more meaning, I would like to map those to 3D and minus 3D. Now that means I'm going to put more symbol power into the transmission, which means I have higher SNR and lower probability of making a mistake. So I can only make a mistake if I look at what happens at an outer level. Then I can only make a mistake in one direction, so my probability of error is just the Q function. So it's half the probability of error of an interior point. Okay, so if we can put this together into one formula, so again, if we assume that each symbol is equally likely, then the symbol error probability for M-level PAM is as follows. So first of all, I have what's the likelihood of an interior point? Well, I have capital M points and capital M minus 2 interior points. So the chance that I have an interior point is capital M minus 2 divided by capital M. The probability of an error is 2 times the Q function. The second case, an exterior point, I only have 2 of those. That's it. So the probability of an exterior point is 2 over capital M, assuming equally likely transmission. And the probability of making a mistake is simply the Q function. So if I just combine do the algebra on this one, I get really 2 terms. I get a constant, well not a constant, but a term that depends only on capital M, and then I get a term that depends on the Q function. Right? Now, for this value, what's the possible range of values that this scaling in front of the Q function can take? 0, well, not 0. So let m go to 0. Well, m go to 2. That's as small as we're going to get. So what does that equal when m is 2? Okay, and what if m goes to infinity? It's not always 2. Something's wrong with our analysis. So when m is 2, I'll give you 1. Okay, so 1, and when m goes to infinity, it's 2. That's right. So the range of values here is, this is between 1 and 2. It doesn't change much, honestly. But what's in the Q function changes dramatically. Remember, this is a roughly exponential decay. Versus the argument. So the big change occurs with changes in the argument. Not so much m. But we'll see in just a second that what's in the argument here can be written as a function of square root of s and r, and that's going to actually have a relationship to m. So let's do that. All right, so we can write, if you remember, we can use we had the definition of S and R on the previous slide. All right, S and R was just, again, signal power over noise power, and it had this expression. So if I wanted to rewrite what's in this d over sigma in terms of square root of S and R, then what we'll see is a dependence on m. M comes into play again for this, just from isolating terms. All right, so if I want to isolate d over sigma. And if I do that, it simply means, multiply both sides by 3, divide both sides by the quantity, m squared minus 1, and I get what's here on the argument to the Q function. So the key is that I can write the argument of the Q function as a square root of S and R, or something proportional to the square root of S and R. So again, as S and R increases, I get a dramatic decrease in the probability of a symbol error. Again, it's all linear units for S and R, all this discussion. Okay, again, if I look at the parameters involved here, I have sigma squared, which I don't have control over in a real fielded system, but in simulation I do. What I do have control over in the fielded system and in simulation is half the constellation spacing and number of levels. All right, let's talk about eye diagrams to wrap up the remaining time. Okay, so here's an eye diagram for two-level PAM. And again, we talked about visualizing a periodic signal by taking the plot in the time domain. We did this with a sinusoid. So if I take a cosine that's repeating, and it's hard over, if you just look over a long period of time, it's hard to see subtle distortions in the waveform. And so what we did is we said, well, let's go ahead and take one period and then just superimpose the next period on the first period. And if you do this over time, you'll start seeing, if there's any jitter in the phase, you'll see it. If there's any distortion in the waveform, maybe there's noise being added, you'll see, if you trace this out, you'll see a different, over enough time, you'll see all the distortion over that period of time. Much easier than it's hard if you just plot it as a trace, it'd be hard to visualize. But here, if you superimpose and just trace over every period, and so you go here, and then the next period, gets traced over the first one and so forth, you'll see the distortion. Same thing holds. So this is also the idea with the eye diagram, is that I have, if I use a pulse shape like the truncated sinc or raised cosine, or square root raised cosine for that matter, then what I'll see is over that pulse shape looks like this in a non-causal plot. And so here's my truncated sinc, and this is T sim. This is minus T sim, and that's 2 T sim. And of course, minus 2 T sim. Now, this is my pulse shape, so I'm going to use this to send a stream of symbols. So I get a bunch of overlapping and scaled versions of this pulse shape. This is my basic pulse shape, which in our notation we've been using GFT. So now if I get a transmitted PAM transmission, it's just a weighted combination of these, weighted and delayed and summed. And so if I take a received waveform and I plot it over 2 symbol periods, and the next received part of the signal, I just simply overlap in the first 2 symbol periods. I just keep tracing over again. As I get more and more signal, I just trace over itself. And what I'll see is a shape. You'll see the main hump of the truncated sinc. That's for 2PAM. That's for a symbol amplitude of D, and then this is for a symbol amplitude of minus D. And if there's no noise and there's no sampling mismatch between receiver and transmitter, you get a very clean eye. Now, you also get the tails of the sinc. They're going to add to the next period, so you'll get a little bit of contribution from those tails. Okay. And if there's no noise, you get a diagram that looks like this. And this looks like a human eye. And the more open, the better, because ultimately what we do is that at every point, really at the origin, we're going to take a sample and decide whether it's greater or less than 0. If it's greater than 0, it's a bit of value 1. Less than 0, a bit of value 0. So how good this thresholding is at 0 tells you what's the probability of making a mistake. Here we don't have a probability of error. There's no noise. There's no impairments whatever. We have idealism here. Now, if I start adding some noise to this, then the signal that I get will be some noise riding on top of my sync waveform. And again, I have no impairment on sampling. Okay, still looks pretty good. Now, as the noise increases in power, now the eye starts closing. And eventually, if I get enough noise power, the eye will close. And my thresholding is now getting to the point of a coin flip. The noise is so powerful. It's overwhelming the signal. Now, you can also see other impairments like the change in sampling in the symbol time. If you're off in the symbol time, then what will happen is you'll cut short the 0 crossing, and that will map into an eye diagram. Instead of getting this in the eye diagram, you'll miss this point here, and so you'll miss, this will come, let's say, here instead of 0, and the rest of it will come down. And as the more the miss, this eye will start closing. Okay. So this eye diagram is an empirical way to debug and diagnose problems. You can see the noise, and at least you can get an empirical idea how good is the signal quality at that particular point. You can measure the transmitter output, receiver input, after the match filter. It can be almost anywhere in your system as a debugging tool. Last piece is to generalize this to 4PAM. You'll see 3 eyes now with 4PAM. And if you don't do the eye diagram quite right, you'll see some problems at startup. And this problem at startup is due to what?
Delay.
Which delay?
Group delay.
The group delay, once again. It comes back. So basically, you want to throw out the first few symbols equal to the number of symbol periods in the pulse shape. That's the worst case. The group delay would be throw out half the symbol periods in the pulse shape. That's the group delay idea. Go ahead.
You know how we see 3 eyes? You're saying that it's like n minus one I.
That's right. You'll see m minus 1 i's. That's right. Exactly right. Again, this is a clean signal. There's no, this one I don't think had, I think this one had much noise. I don't see, it does not visually look like there's any noise here. And it's perfect sampling. All right, have a great weekend. No.